Welcome to Industrial PLC Applications. This video is on counters. Another primary control is counting. How much have we made? How many do we have left? What is the current level of inventory? Connected Components Workbench and the Micro 850 have three basic counters: count up, count down, and count up and down.
With counters, it's important to understand how they work in relationship to the processor and the logic scan and execution. To do this, we're going to go back to school for some simple math. I have two equations that appear on the screen. A equals A plus 1. Now in mathematics, that cannot be true, because the equal sign says that both the left and right side are equivalent. They're the same. In order to fix that, we would have to say that A does not equal A plus 1. But in programming, it's a different equation. And the equal sign does not mean that the two halves are the same, but rather make them the same. In other words, A is equal to A plus 1 is actually read and interpreted as make A equal to A plus 1. It's a way of adding to a register and continually adding that amount without having to create multiple registers. I'm going to jump to another instruction to help clarify what happens with counters, since they basically add by 1. The add instruction works with two simple data types and adds them together. The value stored at the variable location or fixed amount of I1 is added to the value at location I2, and then the result is stored at location identified in O1. So let's watch these two add instructions. We'll focus on the top one in rung number 2. I'm going to flag the input, digital input 2, and I'm just going to toggle it on and off as fast as I can. Now, according to what we just heard, it's supposed to take 1, the value of I1, and add it to the value of I2, which had no value, and then put it into the same location called scan count, but we should have got 2 because I only clicked it once, and yet I have a number of 605. On rung 3, the same identical input was used and it was flagged, but look at the result. I clicked it once, the same identical time as the other instruction, and yet it only put in 1. I'm going to flag it again, and the bottom rung 3 is 2, but the top rung says now 1300. The reason that there's a difference between the two is the leading instruction before the add. On the top, we find our usual execute if charged. But on the bottom, we have a new instruction that says ONS. Now this is also known as the pulse instruction. ONS is the older version that the old name for it that was used in control logics. And on Connected Components Workbench, you can elect to use the logics theme, and for all the math and compare instructions, the font they used to identify the instruction is so small it's hard to read. So when I'm working with them, I flip to the logics so I can actually see the word add, or greater than or equal to, or some of the other comparative statements. So this ONS, otherwise known as a pulse instruction, only examines that input for one single scan, whereas a regular execute if charged always does it because it has to. It's constantly, every scan, it has to be monitored to make sure whether it is still true or whether it is whether it's become false. So Rung 2 actually kind of becomes a scan counter. From the amount of time it took me to push that button and release it, it counted 605 the first time, and then the second time was a little longer. We now have 1300 in our count. So we cannot use the XIC instruction as a means of counting. We'd have to use a pulse instruction. But fortunately, we don't have to worry about this. Let's take a look at their actual counter.
All connected component workbench counters, regardless of function, share one key common trait. They are all embedded with a pulse or one-shot input to trigger a change in the collected value. Every counting input trigger only works if this instruction sees a false to true transition and then a true to false transition. Let's look at a typical count. First, the input is low, so there is no count. Then, the input goes high. A false to true transition has taken place. We have followed the rising edge. Therefore, 1 is added to the current value stored. Then, although the input remains true, there is no further change to the current value. When the input goes false, a true to false transition has taken place, a falling edge. Therefore, the input is set up for the next count. At the next false to true transition, another 1 is added to the current value. All counters, like their cousins, timers, are constructs, data types that contain a package of other data types, and inherent background logic to operate. The CTU count-up counter, for example, has 4 bools and 2 dints in its construct.
Okay, let's begin by looking at the basic operation of a count-up counter, or CTU. Every time this instruction's .cu input is activated, it adds 1 to the value stored in the counter's .cv memory location. Then, PLC compares the PV value against the CV value, and if the two are equal, the instruction turns on the output Q.
So let's look at the 3 input variables that affect a count-up counter. .cu is the monitored input that will trigger a count. In this particular case, we're looking at input IOEMDI26. When that is true, then our CTU_1.cu is true, and that will trigger a change in the value of our CV. CTU_1.reset is the monitored variable that will trigger a clearing of the stored current value. And in this case, we're looking at input DI24. The CTU.PV is the memory location where the desired maximum counted value, or the programmed value, is stored. The CTU counter has 2 output variables. Its .CV is the monitored memory location that is incremented or cleared by the instruction. In this particular case, it's left blank because we won't see anything until the counter is being programmed. The CTU_1.Q is its output coil. So internally, when it's true, it's going to turn on an output coil. And that is set when our programmed value, PV, equals the current value, CV.
All right, so let's take a look at this count-up counter. And we're going to toggle it, and it has a program value of 5, and the current value will change and it will rise. And then the Q bit will be turned on once the PV and CV are the same. So I'm going to press on and off. And once it reaches 5, I can continue to change that input, and it's not going to exceed that value. Now, on the reset, we have digital input 13, and it says it's false, and that's because we haven't activated it to reset the value. So let's do that. Turn off our input, and we'll hit the reset. It's true, and that's important to know, because if later on you start to try to count, every time you're counting, it's not counting because the reset is true. So you have to make sure that that is either a momentary contact, or you might want to not count for a period of time. That's entirely possible, in which case you would turn on the reset. Notice that the pulse input .p_cu latches until the input attached to .cu goes false again. This unsets the P_cu pulse bit to allow the next false to true transition to add another 1 to the current value. Now that we've seen how a count up counter works in the basics, there are a few rules that we should be aware of when dealing with any counter. So first of all, counters will not pass the programmed value stored. If you want it to count to 100, you can keep hitting the input, but the current value will not go past 100. Once the cue is set, no more counting occurs. Second of all, with counters, they will not count in negative numbers. Now, you can insert a negative value for a countdown counter to count to, but the software and the PLC will stop counting at 0. So you can't actually count negative numbers. With the counters, depending on whether it's the up or down, the count up or count down bits, the reset or the load bits, which we'll get to, all must be bools, just a 1 or a 0. With the current program value and the current value, they must be of the same data type, which by default is a DINT. However, they do not have to be stored only in the instruction. In our last video of our series, we're going to cover how you can actually store different process variables or program variables, and where you can actually refer the current value to other parts of your logic. That's a lot of information to absorb, but who's counting? So, in part 2, we will continue with our CTD, which is the count down counter. In part 3, we will look at the CTUD, the count up and down counter. And in the last video of our series, we will look at manipulating the program value and the current value by way of nominees. Until then, thank you for watching, and see you next time.